Welcome to this class. I am Ramesh, working as an assistant professor in the Department of Aerospace Engineering. In today's session, we are going to learn about the composite section in solid mechanics. First of all, we should know what is a composite section. Composite means it includes, it contains more than one material. So that here how the materials will be shared the load when it is acted upon a load, how the loads are contributed to each material as well as the stress also. So what are the concepts involved in this composite section? That is the thing we are going to discuss in this class. Let's come to this. Here we are having a composite section. This center rod is called having a material steel. Let's take this is a material steel, and the outer material is a hollow tube that is made up of another material called as copper. Let's take copper is a tube. This is also copper. So here the steel, the material steel is inserted in the outer material, inside the outer material called a copper tube. Then it is folded together and a load is applied on it. The load P is acted upon the composite section. So what happens in the load distribution to the copper as well as the steel? First we should have the specification of this steel. Let's have steel. Here the steel is a solid material having diameter D suffix S. Let's take the diameter as ds. And what about the area? The area of steel is, let's take the cross section. Cross section is a cylindrical one. So the cylindrical one means the cross section is a circular one. So pi d square by 4 is the area. Here the diameter only is we are going to apply ds as well as the copper. Okay, as well as copper tube. Now let's go to the copper. Copper, since it is a hollow one, we should have inner diameter as well as the outer diameter. So the inner diameter is, here the inner diameter exactly equal to the diameter of the steel. Since it is fastened together, both the steel as well as the copper fastened together, so the inner diameter of the copper is equal to the diameter of the steel. So I can say that the diameter of the inner diameter of the copper, which is equal to diameter of the steel. Okay. Then the outer diameter of the copper, let's take this as D naught. Okay. Then how to find the area? Area is equal to pi raised to 4. Since it is the copper tube as a hollow, so it is this outer square minus the inner square. So that is the thing is how to find the area of both the material. Okay. What is the concept in this composite section? That's the thing. When the load is applied on the material, it will tend to deform. But here both the two materials are there. Since it is a composite section, it acts as a single unit. So when you apply the load, it will deform as a single unit. So the deformation or the stretch of that two material both will be the same. As I am telling us the change in length. Let's take the length as initially take the length as L. Okay. So the length of steel as well as the length of the copper both are same. Okay. As well as I told you as well the concept, the change in length delta L is that is equal to delta L C. Okay, change in length in the steel as well as change in the length in the copper both are same. Okay, put together we can say that the strain strain equal to change in length by the original length. So strain also equal. Okay, for steel as well as the copper, both are same in the composite section. Okay, then how to find the load distribution as well as the stress distribution? That is the thing. Since we are having strain, we can start with the Hooke's law. Okay, so Hooke's law what it says? Stress by strain equal to stress by strain equal to Young's modulus. So from that I need to know the strain. So strain equal to stress by Young's modulus. So that is the concept from we are going to apply. Okay. So I am going to apply strain in terms of stress. Okay. And one more thing, just I am just a bit of this one. One more thing, the total load acting on the composite section is equal to the load carried by both the materials. That is sum of the load carried by steel plus load carried by the copper, PS plus PC. That is the another concept here. From that only we are going to find the stress as well as the load. Okay, from load I know that stress is equal to load by area. So here load is there. So load equal to stress into area. So I am going to convert load in terms of stress as well as strain in terms of stress. So I am going to put everything in terms of stress only. Okay. So keep in mind that I am going to find. Okay, I am going to find this one. The stress. How to differentiate now? So ES, okay, that's nothing but sigma S by Young's modulus of the steel. Okay, that is equal to strain in the copper. So the stress in the copper to the Young's modulus in the copper. Okay, from that I can find what is the ratio between the stress. So sigma S equal to ES divided by EC into sigma C. Okay, from that I am coming to get our conversion. So ES, Young's modulus of steel as well as copper. So Young's modulus is the material property. It depends on the value. It resists the deformation. If the strength is higher, the Young's modulus value is higher, it gives more strength towards the deformation. Okay, so I will get a value, the Young's modulus, one value I will get that value into this much time, sigma C. Okay, if it is 200 is converted, then it will be 2. That means sigma S, that is the stress in the steel, which is equal to 2 times the stress in the copper. Like that I can get a relation. Okay, stress relation. Then we can apply into the load. Okay, we can apply into the load. Here load, the total load is the known value. I am applying about 50 kilonewton like that. So P S plus PC, that is equal to the total load. The total load is the known value. So I can convert this one as sigma S into area of the steel, as well as here also the stress into area, say for the corresponding material is also equal to P, that is the known value. Okay, here area of steel is also known, area of copper is known. No more thing, I am having sigma S in terms of sigma C. So I am converting here also the sigma S, some value into sigma C into area of steel plus sigma C into area of copper. Okay, that is equal to load. So here it is known value, it is also known value, it is also known value. Okay, in this equation I know all things except the stress value. So from that the sigma C, that is stress in the copper, I can find. Okay, I find the sigma C. By using the sigma C, I can find also, yeah, you can apply this one. Okay, get the value of sigma C, apply here, I can get the sigma S also, that is stress in the steel. I can find. Okay. Now I found all the stress distribution in the materials. Then how to find the load? Okay. Since load equal to stress in the area, so I can find the load in the steel is equal to stress into area. You apply the corresponding value for the given material. So sigma S into AS. Find the value. Okay, you can get the load shared or distributed to the steel, as well as PC for the copper. Then you use same thing, sigma C into area of the copper. Okay, so I can find both the things. So PS, PC. Okay, so known value. Okay, so that's all. If you add this load PS and PC, that is equal to the total value. If it is given 50,000, the value can be that is the left hand side from right hand side. The value. Otherwise, the thing is what you have marked is wrong. Okay, you have to check one side like this. Okay, so this is about the composite section, how load is shared between the two materials, as well as the stress distribution between the two materials in the composite section. If more than 2 minutes are given, the same format only have to approach. One of the thing is the change in deformation. The change in length will be equal to same. Then we have to look at another topic with the. We have to see different topic in the next class. Thank you.